Welcome to the video lecture for section 3.2, measures of variation. This is for statistics, STA 2023, and my name is Jorge Young. So the key concept, variation, is the single most important topic in statistics. So this is the single most important section of this book. Now this section presents three important measures of variation, which is the range, the standard deviation, and the variance. Now, these statistics are numbers, but for our focus is not just about computing the numbers, but developing the ability to interpret them and understand what they mean in context of the data set that we have. So first off, the round-off rule. When rounding the value of a measure of variation, carry one more decimal place than present in the original set of data. Same thing that we did for the mean. Now, we've already calculated the range, but now here's the range. It is a measure of variation, and the range is simply the max value minus the minimum value. And so it gives you some idea of your data set in front of you. So some important properties of the range. The range only uses the max and the min, so it's very sensitive to extreme values. The range is not resistant. Because the range only uses a max and min values, it does not take every value into account, and therefore does not truly reflect the variation among all of the data values. And so how do we find the range? Here's the information for the data set that we used previously. And so the max value is 55.6, the minimum value is 14.1, so then the range for this particular data set is 41.5. And so let me just show you real quick how to calculate that using Excel. And again, we've done this already, so if I wanted to do that, I would just simply do the max minus the min. And of course, we do have other ways of doing this, and I will show you that in class. So the next thing we're going to talk about is the standard deviation. And the standard deviation of a set of sample values denoted by lowercase s is a measure of how much data values deviate away from the mean. So some notation, lowercase s is a sample standard deviation. Sigma is the population standard deviation. So the formula for standard deviation for a sample is s is equal to the square root of the summation of x minus x bar squared divided by n minus 1. Now the shortcut formula that we're going to be using is the following here, which is the sample standard deviation is equal to the square root of n times the summation of x squared minus the summation of x squared divided by n times n minus 1. And we are going to be using that one, and I'll show you how to do that in Excel. And so some important properties of standard deviation. Standard deviation is a measure of how much data values deviate away from the mean. I like to call it the average distance the data point is from the mean. The value of the standard deviation, s, is never negative. It is 0 only when all of the data values are exactly the same. Now, larger values of the standard deviation indicate a greater amount of variation. Now, the standard deviation can increase dramatically with one or more outliers. Now, the nice thing about the standard deviation is that the units are the same as the raw data. Now, the sample standard deviation, S, is a bias estimator of the population standard deviation sigma, which means that the values of the standard of the sample standard deviation do not center around the value of sigma. So here's one way of calculating. We're going to use the sample data that we've been using. And so we get a sample standard deviation for these 5 points of 16.45. And so if we were to do the other formula, we would still get 16.45. So regardless of which one you use, you will still get the same value. And so let's see what that looks like using Excel. And so I tend to use SD when I use it in Excel. Here's the formula that we're going to use. And so the first thing that I'm going to do is I'm simply going to have all of my x values, which are these values here. I'm going to add those up, and I get 153.7, which is exactly what they got when they did it here. So this part right here is just the summation of x. And so the next thing I'm going to do is I'm going to go ahead and square each one of these. There's 2 ways that I can do it. Simply just multiply it by itself. Or I can also use the caret key, and I'll still get the same value. And then just go ahead and drag it. And so I get 5,807.8, which is exactly what they got in the PowerPoint. And so we're going to use this formula here. In this case, n, I have 5, so I have 5 data points, so my n is equal to 5. And so when you start putting this in here, it gets a little tricky, so you have to be careful. We have to use multiple parentheses. So 5 is my n times, this is my summation of x squared, minus this value, and I'm going to use the caret key just for spacing issues. And so you can see that that's my numerator, which is 5 times my 5,807.8 minus my 153.7 squared. And now I'm going to go ahead and divide it. I'm going to use parentheses again, and this is going to be 5 times 5 minus 1. I could have just simply done 4. And so what you're looking at here now is the formula that's there in front of you in Excel. And so just double check the parentheses and make sure that our parentheses are fine. And you can see that I am missing one. And now once I do that, now all my parentheses are grouped in pairs, which is what we need. And then we press enter and we get 16.458, and we just simply want this to go to 2 decimal places. And so we get 16.5, which is exactly what they got in the PowerPoint. And so we can also calculate this using Excel, and there are several ways. I'm going to show you one way here in the video and then one way in class. So if I start typing ST, you notice that I get standard deviation.s. That's for my sample. Standard deviation.p. You'll notice in a moment that the formula is slightly different for each one of these. So this is a sample. I'm going to go ahead and use the sample one. And then you notice that we actually get the same thing that we got before. And I'm just going to go ahead and round that to 2 decimal places so you can see. So this is the long formula, and this is the quickest way of doing it. Also, when we find the standard deviation of frequency distribution, we do use this formula right here. And so some range rule of thumb for understanding standard deviation. The range rule of thumb is a crude but simple tool for understanding and interpreting standard deviation. Now, the vast majority, such as 95% of sample values, should lie within 2 standard deviations of the mean. Again, this is for a data set that's approximately normally distributed, or it is normally distributed. So some rule of thumb, and so if you have values that are lower than the mean minus 2 times the standard deviation, or you have values that are mean plus 2 times standard deviation, those are what they consider to be significantly high or low values. Now, if it's between mu plus or minus 2 sigma, then those values are not significant. So if everything else is equal, 95% of all of your data points should be between this value and this value. Again, range rule of thumb, to roughly estimate the standard deviation from collection of known sample data, we can use the range divided by 4. If we were to do that using the information, the data set that we've had before, and so we know that this is our range. If I divide that by 4, you see that it does underestimate by a lot the standard deviation. So it is a very crude value, and if you have technology available, there's no need to find it that way. Now, standard deviation of a population. Now, different formulas used to calculate the standard deviation sigma of a population. So instead of dividing by n minus 1 for a sample, we simply divide by the population side, capital N. Now, the variance of a set of values is a measure of variation equal to the square of the standard deviation. So the sample variance, S squared, is the square of the standard deviation. Population variance, sigma squared, is simply the square of the population standard deviation. So if we find the standard deviation, whether it be a population or a sample, we can simply square that to find the variance. So here's some notation. Lowercase s is sample standard deviation, s squared is sample variance, sigma is the population standard deviation, and sigma squared is the population variance. Now, the units of the variance, or squares, of the unit of the original data values, it's difficult to kind of connect them, if you will, as opposed to the standard deviation, which is the same units. The value of the variance can increase dramatically with the inclusion of outliers, so the variance is not resistance. The value of the variance is never negative. It is 0 only when all the data values are the same number, and the sample variance, S squared, is an unbiased estimator of the population variance, sigma squared. Now, why do we divide by n minus 1? This is what they call degrees of freedom. So there are only n minus 1 values that can assign without constraint. Now, with a given mean, we can use any numbers for the first n minus 1 values, but then the last value will be automatically determined. Now, when we divide by n minus 1, sample variance as squares tend to center around the value of the population variance sigma squared. With division by n, sample variances as squared tend to underestimate the value of the population variance sigma squared. So that's why we divide by n minus 1 as a better estimator. Now, next thing we want to talk about is the empirical rule. So, and this really relates to what I said before about the 95%. It really has to be a bell-shaped distribution for us to sort of talk about the 95%. So the empirical rule states that for data sets having a distribution that is approximately bell-shaped, the following properties apply. About 68% of all the values fall within one standard deviation of the mean. About 95 of all the values fall within 2 standard deviations of the mean. And about 99.7% of the values fall within 3 standard deviations of the mean. What that tells us is that anything greater than 3 standard deviations or lower than 3 standard deviations from the mean are really, the probability of that is really small, and those are really extreme values. So here's a graphical representation of the empirical rule. And so when we say one standard deviation, so here's the mean, x bar, sample mean. So x bar plus s, which is x bar plus the standard deviation, or x bar minus the sample standard deviation. So 68% of all the data points should be between whatever this value is and this value. 95% should be 2 standard deviations away from the mean, either plus or minus. 99.7 should be plus or minus 3 standard deviations away from the mean. And you can see that each one is broken up further into percentages. Now, here's an example. IQ scores have bell-shaped distribution with a mean of 100 and a standard deviation of 15. So what percentage of IQ scores are between 70 and 130? So the key here is to recognize that 70 and 130 are each exactly 2 standard deviations away from the mean of 100. So 2 standard deviations will be 2 times s, which is 2 times 15, which is 30. So 2 standard deviations from the mean would be 100 minus 30, which is 70, or 100 plus 30, which is 130. So given this information, about 95% of all IQ scores should be between 70 and 130. The next one is Chebyshev's theorem. So the proportion of any set of data lying within k standard deviation of the mean is always at least 1 minus 1 over k squared, where k is any positive number greater than 1. Now, when k is equal to 2 and 3, we get the following statements. At least 3/4 or 75% of all values lie within 2 standard deviations of the mean. And at least 89% or 8/9 of all values lie within 3 standard deviations of the mean. And so I tend to like this one better because this applies to a data set that's not necessarily bell-shaped. The bell-shaped, if it's bell-shaped, that 68, 95, 99.7, I mean, those are usually right on the money, regardless of the kind of data set you have. But this one here actually applies to pretty much a wider range of data sets, if you will. So here's an example. IQ scores have a mean of 100 and a standard deviation of 15. So what can we conclude from Chebyshev's theorem? So applying the theorem with a mean of 100 and a standard deviation of 15, we can reach the following conclusions. About 75% of the IQ scores are within 2 standard deviations of the mean. And about 89% of all IQ scores are within 3 standard deviations of the mean. And that means it's between 55, IQ score of 55 and an IQ score of 145. The next thing is comparing variation in different samples of populations. So this is the coefficient of variation. Coefficient of variation, or CV, for a set of non-negative sample or population data expressed as a percent simply describes the standard deviation relative to the mean and is given by the following formula. So for a sample, is a sample standard deviation divided by x bar times 100. For a population, is sigma divided by mu times 100. So we round coefficient of variation to 1 decimal place, such as 25.3%. Now, biased and unbiased estimators. The sample standard deviation, S, is a biased estimate of the population standard deviation, S, which means that the values of the sample standard deviation, S, do not tend to center around the value of the population standard deviation, sigma. The sample variance, S squared, is an unbiased estimate of the population variance, sigma squared, which means that the values of S squared tend to center around the value of sigma squared instead of systematically tending to overestimate or underestimate sigma squared. And that's the end of 3.2. Thank you.